For the past several months, astronomers all over the world have been trying to answer one question that sounds simple on the surface, but becomes almost impossible the moment you look at the data. What exactly is 3I Atlas doing inside our solar system? From the moment of its discovery, nothing about this object has behaved the way a normal comet should behave. Not its brightness, not its motion, not its structure, not its response to sunlight, and certainly not its acceleration. And the closer we look, the more the picture shifts from a harmless comet passing by to something that seems to be following a plan we were never meant to see. When 3I Atlas was first detected, most of us expected another Oumuamua-like visitor, a passive object drifting through our system on its way back to deep space. But the early observations already hinted at something different. The object was unusually stable for something that small and that distant. It showed almost no natural wobble, no chaotic light curve, and no unpredictable tumbling. Comets usually behave like cracked icebergs, irregular, spinning, with light scattering in ways that change hourly. Atlas, on the other hand, behaved more like a manufactured body with a balanced mass distribution. It moved smoothly, its changes were controlled, its brightness did not flicker without reason. Soon after the first weeks of observation, ground-based telescopes followed by space-based platforms began recording a glow on the sun-facing side of the object. That glow was stable, sharp, and unnaturally consistent. Natural comets form a coma that expands away from the sun as gas and dust evaporate. Atlas showed something different, a teardrop-shaped brightness that pointed into the solar wind instead of away from it. At first, the team wanted to believe it was an illusion, an optical effect caused by viewing angle or dust alignment. But as more data arrived from 4 different continents, the pattern remained. The glow was real, it was shaped, and its orientation was the opposite of what physics predicts for a natural comet. The more we tried to explain it, the less sense it made. Material simply does not move toward the sun under normal conditions. The solar wind and radiation pressure push everything away, sometimes violently. For dust or gas to hold a stable shape in the opposite direction, some form of counteracting force must exist. Not random outgassing, not chaotic venting, but something steady and persistent. Something that can resist the solar wind instead of surrendering to it. For weeks our team kept repeating the same question. What natural process can push material into a headwind of hundreds of kilometers per second and hold that line cleanly, like a beam? We still do not have a natural answer. Then the next problem appeared. As the object approached its closest point to the sun, all the major observatories on Earth fell into a blind spot. The sun was directly between us and the object. For 2 critical weeks we had no clear view of what Atlas was doing. In those weeks, sunlight was transforming its surface, heating it to the highest temperatures it would ever experience inside our system. That is the moment when natural comets behave most violently. They fracture, brighten, fragment, unleash massive plumes. Some disintegrate completely. We should have seen chaos. But by the time Atlas came back into view, it did not look damaged. It did not look unstable. It looked deliberate. The brightness pattern became sharper, more structured. The strange sunward teardrop was still present, stronger than before, and most important of all, its trajectory had changed in a way we could measure precisely. The object began drifting off its predicted gravitational path by a small but undeniable amount. That drift was not random. It did not wander back and forth. It increased smoothly, exactly in proportion to how much sunlight the object received. Every time the sunlight increased, the acceleration increased. Every time the sunlight decreased, the acceleration slowed. This was the most disturbing part because that pattern acceleration following sunlight in a perfect inverse square law is exactly how sunlight itself behaves. The same pattern you see in solar sails, solar panels, or any technology designed to use photons as a source of propulsion. Natural comets do not accelerate in that way. When they outgaze, the acceleration is chaotic. It depends on the position of vents, the rotation of the nucleus, the direction of active jets, and internal pressure pockets. But Atlas was accelerating as if it were absorbing sunlight and converting it into thrust with almost mathematical precision. We ran the numbers repeatedly. At about 270 million kilometers from Earth, the displacement caused by this acceleration should have been around 54,000 kilometers. When new observations arrived, The measured displacement was almost exactly that. The match between prediction and observation was so precise that it left no room for coincidence. Something was controlling the acceleration. Something was correcting the trajectory. Something was adjusting itself in a way that does not belong to a loose icy body from the edge of another star system. Around this time, independent astronomers began capturing high-contrast images using stacked exposures. Those images revealed details that shook even the most skeptical members of the team. Surrounding Atlas was a long, faint structure, almost like a halo that extended far behind it. That structure did not behave like a tail. It did not disperse. It did not distort the way a dust cloud should distort. Instead, it held its shape with surprising stability, even as the object rotated. At first, we thought it was an imaging artifact, but after multiple observatories reproduced it, we had to accept it. The tail was not a simple plume. It was a structured formation. This led to the swarm hypothesis. If Atlas was surrounded by a cloud of microscopic reflective particles, lightweight, stable, and distributed in a controlled pattern, it would solve several mysteries at once. A swarm like that could increase the object's brightness enormously without requiring a large reflective solid body. It could hide the true size of the nucleus. It could smooth out the light curve, conceal rotation, and mask structural features. It could also serve as a light amplifying surface, boosting the effectiveness of any sunlight-powered propulsion system. If the swarm contained only 0.1% of the object's mass, it would still reflect up to 100 times more light than the nucleus itself. In other words, most of what we were seeing was not coming from the object. It was coming from the material around it. And that raised a far more important question. Why would an interstellar traveller surround itself with a reflective swarm? One reason is protection. Another is concealment. A swarm can serve as both a shield and a disguise. It hides the true shape, size, and structure of the core. It makes the object look natural from a distance. It can even mimic comet-like behaviour if needed. For all practical purposes, a well-controlled swarm could make a technological structure appear like a harmless comet until the moment it chooses otherwise. Of course, natural explanations still needed to be examined. We looked at every possibility: unusual ice composition, extreme sublimation patterns, rare grain sizes, rotational stability anomalies. We tried to force the natural comet model to fit the data. But piece by piece, the natural model collapsed. It could explain one anomaly at a time, but never all of them together. There was no single comet-based mechanism that could produce a stable sunward glow, mathematically precise solar-driven acceleration, a persistent reflective swarm, and a near-perfect trajectory adjustment during a period when all our instruments were blind. And so, the picture began to shift. This was no longer an analysis of comet behaviour. It was becoming an investigation into what an interstellar probe might look like if it tried to disguise itself as a comet. If you were an advanced civilization sending an object into a foreign star system, you might want it to appear ordinary, you might want it to blend in. The easiest disguise would be something the target civilization already expects to see, an icy visitor from another star. Then you would surround your core with reflective particles to mask its shape. You would rely on sunlight for propulsion to avoid producing chemical exhaust. You would activate your systems behind the sun, when observers in that system are blind. And you would accelerate slowly, carefully, using natural forces to minimize detection. This interpretation is not proven, but the deeper we go into the data, the more it describes exactly what we would expect from such a design. And that brings us to the real question: what is 3i Atlas preparing for as it moves deeper into our system? Because everything it has done so far, every acceleration, every structured glow, every carefully timed shift points toward intention, not accident. And intention means mission. As 3i Atlas moved farther from the sun and deeper into the region, where our observatories could finally track it without interruption, another detail emerged. Something subtle at first, but increasingly important the more closely we examined it. The object was not simply drifting along a predictable path. Its trajectory showed signs of continuous fine-tuning, almost as if it were following a set of instructions rather than obeying the natural forces acting upon it. And what made this so unsettling was not just the smoothness of the corrections, but their scale. They were tiny, almost delicate, yet perfectly timed. They nudged the object in ways that only became visible when we compared long windows of data, compiling weeks of motion into a single curve. Normal comets do not behave this way. Their path is shaped by gravity, and their deviations are shaped by chaos venting, rotation, fractures, unpredictable pressure pockets. These deviations rarely stabilize. They jitter, they wobble, they fade, they sometimes reverse direction entirely. But 3i Atlas showed none of this noise. Each deviation maintained a steady sign. Each shift matched the solar input. Nothing contradicted the pattern. Nothing wandered. It behaved less like an object being pushed around by nature and more like a system that was aware of where it needed to go and was making gentle, constant adjustments to reach that destination. When we tracked those adjustments forward, something new appeared. The object was guiding itself toward an extremely narrow corridor in the outer solar system, a corridor that would eventually bring it into a gravity environment where small corrections matter enormously. The zone where the pull of Jupiter starts to balance against the pull of the Sun. In this region, even a minor change in direction or velocity can determine whether an object continues outbound, enters a stable orbit, or drifts into a long-term path around the planet. And here was Atlas steering toward that boundary with a precision that defied chance. Long before the encounter with Jupiter, the object also began showing a pattern in its brightness that was completely separate from what we had seen earlier near the Sun. It would dim slowly, then stabilize, then brighten again with a timing too regular to dismiss. These were not explosive outbursts. They were controlled transitions, almost like calibration cycles. Whenever the brightness shifted, the swarm structure around Atlas shifted with it. At high brightness, the swarm expanded and smoothed out, becoming more reflective, more uniform. At lower brightness, it tightened into a compact shape, revealing sharper edges in the intensity profile. This is not how dust clouds behave. Dust follows temperature, not timing. But something around Atlas was cycling in a predictable way, as if the object were adjusting a system that depended on light distribution. The idea that the swarm could be actively shaped rather than passively floating gained traction quickly. If the particles responded to electromagnetic fields or electrostatic forces, they could be moved into patterns intentionally. Such a system could serve multiple purposes: shielding, temperature regulation, propulsion enhancement, or even communication. And this theory gained further support when we noticed another anomaly, one that had been hiding in the noise for weeks until someone finally isolated it. Every brightness cycle was followed by a slight improvement in trajectory stability. Not a dramatic one, but consistent. It looked as though the object was correcting itself after each calibration sequence, refining its path more precisely with every iteration. If this were a natural process, it would be inexplicable. But if the object were using sunlight both for power and guidance, then periodic adjustments would make sense. It would need to reconfigure its swarm, redistribute reflective material, and recenter its core to ensure that each new segment of the journey matched its intended plan. Of course, at this point we began comparing Atlas to known examples of controlled solar-propelled system solar sails, light pressure experiments, small-scale tests conducted in Earth orbit. The similarities were striking. Solar sails do not produce violent thrust. They produce slow, steady shifts over days or weeks. They require calibration cycles. They rely on careful distribution of reflective surfaces, and they often exhibit exactly the same pattern of acceleration dependence that we saw in Atlas. More sunlight equals more thrust, always following the inverse square law. But Atlas had one massive advantage over anything we have ever built. It did not need a single rigid sail. Its swarm could act like a distributed sail surface, adjusting itself dynamically to maximize efficiency. If sunlight hit the swarm unevenly, the particles could rearrange themselves to maintain a stable force. If radiation pressure increased, the swarm could tighten into a compact lens-like shape. If the object needed more acceleration, it could expand the swarm to catch more photons. A rigid sail cannot do this. A natural comet cannot do this. But a controlled swarm can. We had entered a phase where the data no longer supported accidental explanations. Every new observation added another layer of precision. Every anomaly connected cleanly with the others, and the emerging pattern was one that no natural comet in scientific history has ever shown. Even more disturbing was what happened when we revisited the period Atlas spent behind the Sun, the days when we had no direct observations. When we modelled the trajectory backward using only the post-perihelion data, The object's path showed an unmistakable signature, a maneuver. Not a large one, but efficient. A correction that changed the long-term trajectory just enough to guide Atlas toward the outer system corridor we now see it approaching. And that correction occurred exactly when the object was hidden from our instruments. It is important to understand what this means. A maneuver performed behind the Sun has two properties that make it significant. First, it is invisible to direct observation. Second, it is maximally efficient due to the gravitational environment. If sunlight is being used as propulsion, the deep solar region offers the strongest photon density. If any kind of rotational or structural adjustment is being made, the intense heating near perihelion is the best moment to do it. Everything about this timing fits the behavior of a system designed to avoid detection while optimizing performance. But what really pushed the analysis in a new direction was the discovery that the swarm itself behaves differently depending on the region of space the object enters. In areas with higher solar wind pressure, the swarm tightens and becomes more compact. In quieter regions, the swarm expands. This is exactly how a defensive or adaptive system would behave. It reduces its cross-section when the environment becomes harsh, and expands when it becomes optimal for control or observation. Around this same time, a colleague noticed something that many of us had missed. The swarm is not centered perfectly around the nucleus. It is offset slightly, consistently, measurably. This is not something dust does on its own. It suggests that the object inside the swarm is controlling its distribution intentionally, keeping more particles on one side than the other to generate directional thrust. A perfectly symmetric swarm would produce no net motion. An asymmetric one produces a push, and Atlas has been asymmetric since the earliest images. By the time all these elements were combined, trajectory control, brightness cycles, swarm asymmetry, inverse square acceleration, sun-facing glow, behind-the-sun maneuver. The natural model for Atlas had effectively collapsed. There was no configuration of icy fragments and dust jets that could reproduce these patterns. And so, the conversation shifted once again, this time to a question many on the team had resisted from the start. If this is a probe, what is it doing here? There are several possibilities and none of them are comforting. The simplest is reconnaissance. A probe passing through our system could map planetary fields, monitor electromagnetic activity, gather chemical data and update long-range databases. But Atlas has shown more structure and more strategy than a simple observer would need. Its path is careful, its decisions are subtle, and its behavior suggests long-term planning. Another possibility is deployment. If Atlas carries small devices inside the swarm devices hidden by the reflective cloud, then it could release them at precise moments along its path. These devices could be passive monitors, data relays, long-lived sensors, or dormant units waiting for activation. A distributed swarm around the main body could conceal these operations entirely from our view. A more complex scenario is that Atlas is part of a multi-stage mission, one in which probes arrive at different times or perform different tasks across the solar system. That possibility gained strength after the detection of an anomalous signal on the dark side of the Moon, an event that raised questions about whether our system is already being instrumented without our awareness. But the possibility that concerns us the most is the simplest. Atlas may not be leaving after it completes its mission. It may settle into a long-term path inside our system. Its current trajectory is not purely hyperbolic. It is not behaving like an object that intends to escape. Instead, its small but consistent adjustments bring it closer to the kind of course an object would follow if it planned to remain near a stable gravitational boundary. If that is the case, then Atlas may not be a visitor at all. It may be the beginning of a presence. And that possibility calmly, quietly, in the back of every calculation changes the meaning of every observation we have made so far. As 3i Atlas continued its journey away from the inner solar system, the next phase of observation revealed something that many of us had suspected but hesitated to say aloud. Whatever this object is, it is interacting with sunlight and the solar wind in a way no natural body has ever demonstrated. And the more we monitored it, the more the behavior pointed toward a system that was actively managing incoming energy, rather than passively reacting to it. Most comets break down as they lose heat. They fade, they fragment, and their comi collapse as they move outward. Atlas did not fade, it reorganized. Instead of diminishing, the swarm around Atlas began showing a new pattern. The particles were no longer simply reflecting sunlight, they were modulating it. Observers noticed that the brightness distribution became smoother, with fewer chaotic flickers and more stable transitions. This kind of consistency is extremely unusual. Dust reacts directly to sunlight, and sunlight fluctuates constantly due to solar wind turbulence and internal grain movement. But the swarm seemed to dampen these fluctuations, stabilizing itself like a system that was compensating for environmental changes in real time. This was the moment we realized we were no longer looking at a passive cloud, but at something behaving like an engineered field. The particles were not drifting randomly, they were staying in place relative to one another. Their spacing remained consistent. Their density adjusted depending on the angle of sunlight, and when the solar wind intensified, the swarm contracted slightly, as if trying to minimize drag. This is not how dust behaves, but it is exactly how controlled microstructures behave when they are designed to regulate incoming force. During this period, several independent research groups noticed a secondary signature hidden within the brightness fluctuations. At low brightness, the object's core became more distinct, as though the swarm allowed more light from the center to pass through. At higher brightness, the core became obscured. This suggested that the swarm could thicken or thin on command, changing the transparency of the envelope. A natural comet cannot do this. A comet's coma becomes more transparent only when it loses material or when sunlight weakens, but Atlas was altering its transparency under constant sunlight, showing deliberate control over how much light escaped. This discovery forced us to reconsider the core itself. If the swarm was adjusting transparency, then something inside might require light shielding. It could be for temperature regulation, protecting sensitive components, or even controlling the thrust generated by sunlight. Some members of the team wondered whether the core might contain multiple segments, compartments, panels, or surfaces that interact differently with light. If so, the swarm could serve as both camouflage and energy regulator, modulating the amount of light hitting different areas. At this point, the swarm became impossible to interpret as a simple byproduct. It acted like a dynamic surface. When plotted over time, brightness changes aligned with predictable intervals, almost as though the system inside was performing cycles. These cycles appeared to last several hours each, matching no known rotation period, but matching changes in the object's small-scale acceleration. Each cycle ended with a slight directional correction, tiny but measurable. This reinforced the idea that Atlas was constantly rebalancing itself, updating its heading to stay aligned with a specific long-term trajectory. When we extended that trajectory into the outer system, it led to a prediction that caught everyone off guard. Atlas was heading toward a region where the gravitational influence of Jupiter becomes extremely delicate. If the object arrived with too much velocity, it would simply pass by. If it arrived with too little, it could be captured. But if it arrived with exactly the velocity it currently appeared to be targeting, it would skim the boundary in a way that allows for deployment of stable, long-lived objects, small devices that could drift into orbits requiring almost no energy to maintain. This realization reframed our entire interpretation of the data. Previously, we had assumed Atlas was simply passing through, but now, with each adjustment and each brightness cycle, it became clearer that the object was not heading outward in a straight line. It was aiming for a precise corridor that is difficult to reach by accident, and the only way to reach it with the accuracy shown in the data is through constant micro-adjustments, exactly the pattern we observed. Around this time, another anomaly emerged, one that had been overlooked in earlier analyses: the thermal signature. Infrared data showed that Atlas cooled more slowly than expected after perihelion. Natural comets cool rapidly. Their surfaces return to low temperatures in a matter of days or weeks. But Atlas retained heat far longer, and not evenly. Some regions cooled faster than others, indicating internal heat distribution rather than simple surface evaporation. This suggests that the core may not be a uniform block of ice, but a structure with different thermal properties in different areas. In engineered designs, this happens when separate components radiate heat differently. Additionally, faint spectral lines began to appear at unpredictable intervals. These lines did not correspond to typical cometary gases. They were weak, narrow, and seemed to come from trace particles in the swarm. They might be residues of reflective materials, silicates, carbon structures, or metallic compounds. Nothing definitively unnatural, but nothing typical for a comet either. Of course, without a physical sample, we cannot identify them with certainty. But their timing was unusual. The lines appeared during moments when the swarm reorganized, as if new particles were being released or redistributed. By this point, the question was no longer whether Atlas behaved oddly, but how many of its behaviors could reasonably be considered natural. A handful of anomalies can be explained as coincidence. Dozens of consistent anomalies, working together and supporting one another, cannot. The swarm, the acceleration pattern, the transparency control, the heat retention, the brightness cycles, the behind-the-sun maneuver, they all pointed to a single conclusion. Atlas is operating with intention. What troubled us most was the precision. Natural forces are noisy. They produce jitter, randomness, uneven changes. But nothing about Atlas was random. When we analysed its acceleration curve, we found that deviations from prediction were smaller than those of known spacecraft operating with intentional thrust. This should be impossible. Natural outgassing cannot match the precision of engineered propulsion. But Atlas matched it almost perfectly. This is when the final turning point arrived, the discovery of resonance. A research group comparing brightness cycles to trajectory corrections found that both aligned with a repeating interval. Every cycle lasted nearly the same length of time. The differences were tiny too small for natural processes. In physics, this kind of consistency indicates a control loop, a feedback system making constant adjustments. A natural body has no feedback system, but a probe does. A probe measures, corrects, rebalances, repeats. And Atlas was repeating with eerie consistency. When the resonance was discovered, it unified everything. The brightness cycles, swarm shifts, acceleration adjustments, they were all part of a single system, a regulatory mechanism, a main control loop keeping the object on its intended path. That path, in turn, was leading toward an encounter that could allow the object to deposit whatever it carries into a region perfect for long-term stability. So the question became, what is inside the swarm? The answer is, we do not know. The swarm hides everything behind it. The core is invisible. All we see is reflected sunlight and the behavior of particles. If the core is a solid object, its shape and composition remain a mystery. If it is segmented, we cannot see the joints. If it contains technology, we cannot detect it directly. The swarm acts like a curtain one that only opens when the object needs to regulate incoming light. Despite this, we can infer some things. For example, the swarm would not remain stable unless the core emitted a field of some kind, electrostatic, magnetic, or something more sophisticated. Without such a field, dust would scatter and drift away. A stable distribution means controlled retention, and controlled retention indicates a source capable of maintaining that field. Another inference comes from the maneuver behind the Sun. The object changed its outbound trajectory by a small but significant degree. The change was too smooth to be accidental. It required a coherent force, not a random burst. And because photons were the only available energy source, the correction must have been made by adjusting the swarm changing its shape to modify the direction of light pressure. This means Atlas controls the swarm actively, not passively. As these findings accumulated, the final conclusion became clear. Whatever the core of Atlas is, it is functioning with the precision of a guidance system. And now, as the object continues toward the outer system, the core question becomes unavoidable. What is the purpose of this guidance? Because the data now supports only two realistic possibilities. The first is observation. Atlas could be mapping our solar system in detail, collecting information, scanning magnetic fields, sampling dust, measuring radiation patterns, and sending data back toward the direction it came from. This scenario is plausible. Many of its behaviors are consistent with long-range observation missions. The second possibility is more disturbing. Atlas could be deploying something. The swarm could contain more than reflective particles. It could contain smaller units devices designed to separate, drift, hide, activate later. If that is the case, then the encounter near Jupiter becomes the most important moment in the mission. Not because Atlas will perform something dramatic, but because it might do something that we cannot see. For now, all we can do is watch the object, analyze every data point, and prepare for what happens when it reaches Jupiter. The truth is simple and unsettling. Atlas behaves like a system following a plan, and systems that follow plans rarely travel alone. As weeks passed and 3i Atlas continued its steady movement toward the outer solar system, a new pattern began to emerge, one that forced us to rethink what this object may be preparing for. Until now, we had focused mostly on how Atlas behaved: the swarm, the controlled acceleration, the trajectory corrections, the brightness cycles. But as more long-duration tracking data accumulated, it became clear that all of these behaviors were components of something larger. They were not isolated anomalies. They were steps-coordinated, purposeful, logically sequenced steps that pointed toward a final operation. To understand this operation, we must begin with one of the most overlooked but critical details: the object's stability. Unlike natural comets, which constantly change their apparent brightness and shape due to chaotic outgassing, Atlas remained remarkably consistent across long observation windows. Its swarm changed, yes, but it changed predictably. Its acceleration changed, but it changed in a way that matched the sun's energy. Its course changed, but it changed with perfect continuity. Nothing behaved like noise. Everything behaved like a controlled system. This is important because systems like this do not operate indefinitely without purpose. When a probe travels through a foreign star system, it does not constantly adjust itself unless those adjustments serve a mission. And the closer Atlas gets to the region near Jupiter, the more obvious it becomes that every adjustment has been steering it with extraordinary precision. Natural objects wander, Atlas corrects. The next clue came from an unexpected source: measurements of the object's microvariation response. When exposed to shifts in solar wind density, Atlas does not react like a loose cloud of dust. Instead of scattering or distorting, the swarm around it contracts in a controlled way. The contraction is not instant, it follows a smooth curve. It matches the rate of change in the environmental force. It does so repeatedly. This indicates more than simple resilience. It suggests responsiveness. A responsive field is one that reacts to external conditions in order to preserve internal structure. And only systems with a mission preserve structure that carefully. Another factor deepened the mystery: the absence of rotational chaos. Natural comets usually tumble due to uneven heating, gas jets, nucleus asymmetry, and impacts from solar particles. But Atlas does not tumble, at least not in any detectable sense. Its brightness curve shows no sign of rotation-induced fluctuations. Every time we attempted to isolate a rotational signature, it disappeared back into noise. There are only two explanations for this. Either the nucleus is almost perfectly symmetrical, which is extremely unlikely, or the swarm is masking rotation deliberately. Masking rotation can be useful in several ways. It allows the core to keep specific surfaces oriented toward or away from the sun. It stabilizes thrust efficiency. It protects sensitive components. And most importantly, it prevents outside observers from learning anything about the structure inside. If Atlas were a probe, hiding rotation would be one of the simplest and most effective ways to avoid revealing design details. The next turning point came when teams began analyzing variations in reflected polarization. Light reflected from dust normally shows clear patterns based on particle size and orientation. Comets produce predictable polarization curves because their dust is chaotic. But Atlas did not follow the curve. Instead, its polarization shifted abruptly at certain intervals, always following the same repeating cycle we identified earlier. Each shift suggested that the particles were changing orientation synchronously, as though responding to a field or to commands. Synchronized orientation in a dust cloud is unnatural. It indicates that the particles are being held in place relative to one another. This is consistent with electrostatic confinement systems, a technology we have only begun experimenting with in laboratory plasma devices. The idea that an interstellar object could maintain such a structure across hundreds of meters or even kilometers of space is, by our standards, extraordinary. But the data does not require us to assume advanced engineering. It only requires us to recognize that nature does not do this. At this stage, the most important question shifted from how does Atlas behave to what is Atlas preparing to do. Every pattern, every correction, every field adjustment appeared to be leading toward a specific moment, the approach to Jupiter. And when we modelled the trajectory forward, that moment became unmistakable. Atlas was not simply passing near the planet. It was aligning itself to skim the outermost envelope of Jupiter's gravitational influence, the region where a small shift can determine whether an object enters a temporary orbit or continues outward. Most objects pass this region randomly. Atlas is not approaching randomly. It is approaching as though it must arrive at a certain point with a certain velocity at a certain time, and if this is intentional, then the purpose becomes clear. This region is ideal for releasing long-lived devices that can remain in the system quietly, with minimal energy expenditure. If Atlas intends to release something, Jupiter's outer gravity field is the perfect location for it. At this distance, a small device can be captured into a slow drift. It does not fall into Jupiter. It does not escape into deep space. It remains in a quiet zone, stable for decades, centuries, even longer. Human engineers use similar gravitational boundaries when placing observatories near Earth. Stability is priceless for a passive monitoring device. The next question is, what kind of device could Atlas release? The data suggests several possibilities. One possibility is an extremely small passive sensor, something no larger than a piece of debris, designed to operate silently. If such a device were released inside the swarm, it would be invisible to us. The swarm's reflective particles would mask it completely. Even if the device separated, we would not see it. At Jupiter's distance, our telescopes cannot resolve anything smaller than a city. A meter-sized object might as well be a speck of dust. Another possibility is a relay node. If Atlas is sending data back toward the direction from which it came, a relay node could amplify, route, or stabilize the signal. The placement of such a node near Jupiter would ensure stable long-distance communication without needing constant propulsion. The swarm could easily contain one or more such nodes, ready to deploy. A third possibility is more concerning: dormant units. These would be devices that activate only under specific conditions, changes in our electromagnetic output from Earth, unusual radiation patterns, or even the arrival of future interstellar probes. These devices would not act immediately. They would wait, and they could wait longer than any technology we currently possess. As the object continued its outward trajectory, researchers began noticing that its brightness cycles became increasingly regular. The cycles shortened slightly, suggesting that the object may be preparing for an event that requires the swarm to be in a particular configuration, either compact, expanded, or partially open. This is the kind of preparation engineered devices perform before executing a maneuver. At the same time, the acceleration changes became smoother. The object's path tightened around the predicted corridor. There were no unexpected deviations. This level of control is unprecedented for a natural object, yet completely ordinary for a probe following a pre-computed plan. If the plan includes deploying something at Jupiter, Atlas must approach the boundary with near-perfect precision, and it is doing exactly that. What troubles us now is the combined weight of the evidence. Any single anomaly could be dismissed as noise, but the anomalies do not stand alone. They form a network behavior, timing, trajectory, swarm structure, resonance cycles, compression responses, thermal signatures. Each piece supports the others. Together they leave little room for coincidence. It is becoming increasingly difficult to believe we are observing a simple comet. And when you accept that possibility, even tentatively, a deeper question emerges. How long has Atlas been planning this? If Atlas is a probe, its mission did not begin when we discovered it. It began long before it entered our solar system. Its approach angle, its velocity profile, its perihelion timing, all could have been chosen deliberately to exploit solar energy, gravitational assistance, and observational blind spots. Its use of the Sun as a maneuver point suggests it was aware of how our instruments would fail near conjunction. Its choice of a swarm indicates an interest in concealment. Its smooth acceleration suggests a level of confidence in its systems. Nothing about this mission appears rushed or improvised. It appears rehearsed. This realization leads to the most unsettling conclusion of all. Atlas is not reacting to our solar system. Atlas is executing a mission that already accounted for everything it would encounter here, which means it anticipated sunlight levels, gravitational fields, magnetic conditions, dust densities, and perhaps even the existence of observers like us. Its behavior is not curious, it is prepared. And now, as the object approaches the region where its next maneuver should occur, the final question remains: What will it deploy, and what will remain behind after it continues its journey? Because based on everything we have seen, Atlas is not simply passing through, it is leaving something in its wake. As the trajectory models for 3i Atlas became more refined, and as the object continued its silent path toward the outer regions of our solar system, attention shifted to a pattern that had been present from the beginning, but had never received the examination it truly deserved. This pattern involved not the object's brightness, not the swarm, not the acceleration, but the timing of its behavior. The timing was unnervingly clean. Everything Atlas did, every brightness cycle, every swarm contraction, every micro-adjustment in its path followed intervals too consistent to be accidental. Natural processes can repeat, but they do not repeat with the kind of reliability that we observed here. And as we studied this timing more closely, a troubling realization emerged. The object was not reacting to external conditions, it was following an internal schedule. To understand why this matters, we need to consider what internal timing means for a natural body. A comet has no internal clock. It does not count cycles, manage intervals, or coordinate behavior. It simply responds to temperature, rotation, and sublimation. But Atlas displayed sequences that looked coordinated, not reactive. Each time the swarm tightened, brightness dipped. Each time brightness rose, the object performed a small trajectory correction. These two actions, swarm regulation and course adjustment, always occurred in a fixed sequence, one following the other with a delay so consistent that the margin of variation was smaller than what we see in engineered systems built on Earth. This raised the obvious possibility the object was using feedback loops. A feedback loop is a process in which a system monitors its own behavior and adjusts itself accordingly. For example, an aircraft uses feedback to maintain altitude, a spacecraft uses feedback to point its instruments, a satellite uses feedback to keep its solar panels aligned. If 3i Atlas relies on feedback, then it is capable of measuring something's sunlight, trajectory, swarm distribution, and updating its state in response. No natural comet does this. No passive ice body does this. But probes do. Another key clue came from thermal behavior. After perihelion, the temperature of Atlas should have dropped steadily as it moved away from the Sun. But infrared analysis showed a different profile. Some regions cooled faster, others held heat longer, and the transitions matched the timing intervals of the swarm adjustments. This implies that the interior of the object is not uniform. It may contain sections that absorb heat, redistribute it, and release it intentionally. This is common in engineered systems where internal components must remain within certain temperature limits. And if temperature regulation is happening inside Atlas, then the swarm cycles may be tied to this process opening to release heat, closing to conserve it. What makes this more concerning is that these cycles gradually shortened as the object moved outward. Natural cooling slows processes. Here, cooling accelerated them. It was as though the object's internal operations were preparing for an event that required faster cycling, tighter control, and increased responsiveness. The timing became more urgent, not less. At the same time, the acceleration pattern began showing a faint but detectable variation. The overall thrust still matched the inverse square law, as expected if sunlight were being used as a force source. But small deviations began to appear at regular intervals. These deviations were not random. They formed a repeating shape in the acceleration curve. This kind of pattern is highly unusual. It means the object is adjusting how it interacts with sunlight, not simply absorbing it, but altering the effective area exposed to it. Again, this is exactly what an engineered device with adjustable panels or a dynamic swarm would do. When these acceleration deviations were compared to the timing cycles, the match was unmistakable. Every cycle included a point at which the swarm expanded slightly, increasing the acceleration for a brief period, and then contracted, lowering it again. This kind of modulation has no natural precedent. It is controlled thrust modulation, simple, clean and efficient. By now, the idea that Atlas was simply a collection of dust and ice was untenable. The behavior fit too perfectly into engineered categories: feedback loops, thrust modulation, thermal management, swarm distribution, guided trajectory correction. But the next question that arose was even more troubling. If Atlas is an engineered system, what energy source is it using to drive these operations? Sunlight can produce acceleration through radiation pressure, but operating a structured swarm and internal thermal systems requires more than passive light absorption. There is no evidence of chemical exhaust, no evidence of radio emissions, no evidence of artificial heat spikes. Whatever powers Atlas is silent, steady, and efficient. The simplest explanation is that Atlas is using the swarm itself as both its propulsion and energy distribution system. If the particles are conductive, semi-metallic, or responsive to electromagnetic fields, then sunlight can induce charges, currents, and controlled forces across the swarm. The object could then manipulate these charges to rearrange particles, regulate internal heat, and generate thrust through precise orientation. Such a system would be nearly impossible to detect from Earth. Any emissions would be faint, localized, and masked by the reflective activity of the swarm. Its entire operation would appear natural to observers who are accustomed to seeing comets behave unpredictably. But in Atlas, the unpredictability is missing. Everything is smooth, controlled, and mathematically consistent. This is the signature of a designed system, not a natural one. As Atlas moved farther outward, another anomaly emerged, one that may ultimately provide the clearest evidence of intention. The object began aligning itself with a plane slightly offset from its predicted gravitational trajectory. The offset was tiny fractions of a degree, but it was persistent. Over time, these small adjustments accumulated, shifting the object's course into a new alignment. What made this concerning is that the plane it was aligning with is not random. It is the plane of Jupiter's orbital nodes. This matters because the nodes are where orbits intersect. They are the crossing points where gravitational influence is cleanest, and where transitions between orbital families can occur with minimal energy. If Atlas is aligning with these nodes, it is preparing for an interaction that requires geometric precision, something that could allow it to deploy small objects into specific orbital bands. At this stage, we revisited all available data on the object's interaction with sunlight, thermal energy, acceleration, and swarm behavior. When combined, they painted a picture that was deeply unsettling. Atlas is preparing its systems for deployment, but the deployment is not dramatic. It is quiet, subtle, and nearly invisible. The object is not preparing to release something massive. It is preparing to release something small. Small objects are ideal for long-term missions. They require minimal energy, experience fewer gravitational disturbances, and are extremely difficult to detect. A meter-sized device released into Jupiter's gravitational boundary would be essentially invisible to our instruments. It could drift there for decades without ever being observed, and if multiple such devices were placed at different points along Jupiter's orbital track, they could form a distributed network capable of monitoring the entire solar system from a stable distance. This possibility becomes even more realistic when we consider the swarm itself. If the swarm contains embedded units, tiny sensors, microstructures, nano-fabricated elements, they could separate from the swarm without any visible disruption. The swarm would simply lose a fraction of its density. The brightness might dim slightly. The swarm might tighten or expand to compensate. But from Earth, the change would appear natural. Another troubling possibility is that some of the particles in the swarm are devices themselves. If the swarm acts as a functional system, not just a reflective shield, then its particles might be more than dust. They might be computing units, communication nodes, or environmental sensors. In this model, deployment has already begun. We are watching the distribution process unfold in real time, and because the particles are microscopic, we cannot track them individually. The swarm could shed thousands of units without our awareness. As Atlas approaches the region where its next major adjustments are expected, the cycles continue to shorten. The swarm becomes more responsive, the acceleration becomes smoother, the core remains hidden, and the timing converges toward a point that is not random. It is the approach to Jupiter, an approach that will occur with a precision that no natural comet has ever demonstrated. If Atlas were natural, its arrival would be chaotic. But Atlas will arrive exactly as predicted, and when it does, it will enter a gravitational environment perfectly suited for the final stage of its mission. We may not see what happens there. Our instruments may not detect any change. The swarm may not reveal any opening. The brightness may remain stable, but the absence of visible activity does not mean nothing occurs. The operations Atlas may perform at Jupiter can be small, silent, and invisible to us. And by the time we realize something has changed, the object will already be leaving the system, its mission complete. Whether that mission is observation, preparation, or communication, we still do not know. But everything we have seen so far suggests one thing very clearly. Atlas is not improvising, it is executing. And the timing tells us the next phase is about to begin. As the projected encounter date approached and 3I Atlas continued its precise and unsettling journey toward Jupiter's outer gravitational boundary, many of us began to realize that the most important clues were no longer in the object's current behavior, but in the absence of certain behaviors, specifically the absence of natural instability. Real comets develop fractures, unpredictable jets, chaotic rotations, and violent outbursts as they move through the solar system. Atlas displayed none of these things. It remained intact, controlled, and stable in ways that cannot be explained by luck or by composition alone. Stability of this kind requires structure internal reinforcement, distributed mass, active correction, or some combination of these features. Natural bodies do not hold themselves together this perfectly under such demanding conditions. Even more striking was the behavior of the swarm. As Atlas moved farther into the outer system, we expected the swarm to disperse. Radiation pressure weakens with distance from the Sun. Dust loses electrical charge. Collisions between particles become more probable. Ordinarily, a cloud of small particles spreads out over time, becoming less dense and less coherent. But the Atlas swarm grew more coherent. Its shape sharpened, the transitions between bright and dim phases became less noisy, and the reflective distribution stabilized. This consistency is not only unnatural, it is diagnostic. It shows the presence of a self-maintaining field, one that reinforces the swarm when external forces weaken. Whatever controls the swarm is not fading with distance, it is compensating. This behavior forced us to accept something we had been avoiding. The energy source inside Atlas must be extremely efficient, not powerful in a dramatic sense, but steady, reliable, and distributed. The object is not emitting heat bursts or radio signatures that would indicate active propulsion or communication. Instead, it appears to operate with a quiet, persistent internal mechanism, one that keeps the swarm organized, powers the feedback cycles, and manages thermal gradients. This suggests that the internal systems are not chemical. They may rely on passive energy harvesting from sunlight, or on advanced storage technologies that release minimal waste heat, or even on principles we have not yet developed. The important feature is not the mechanism itself, but the fact that it is intentional. The next anomaly emerged when we analysed the vector of the object's micro-adjustments. In natural comets, forces from outgassing act along random directions, because jets open and close unpredictably. But the tiny course corrections Atlas performs are not random. They always align within a narrow directional band, as though the object is following a long-term guidance map. The band is angled slightly relative to the ecliptic plane, matching the path that leads to Jupiter's ascending node. This alignment is too consistent to be the result of a natural force. It implies that Atlas is navigating, maintaining awareness of its position and orientation relative to a target point. If Atlas has navigation capability, then it must also have sensing capability. Sensing sunlight intensity is simple, but sensing position with respect to Jupiter from hundreds of millions of kilometers away requires more. It requires the ability to detect gravitational gradients, star positions, solar wind variations, or internal gyroscope readings. These are not complex systems by advanced standards. Even our spacecraft carry them, but the presence of such systems in an interstellar object closes the door permanently on the comet hypothesis. At this stage, the question is no longer whether Atlas is artificial. The question is, what level of artificiality are we dealing with? One possibility is that Atlas is a simple probe and automated device launched thousands or millions of years ago, designed to perform a limited set of tasks. But simple probes do not use dynamic swarms. They do not hide their cores. They do not perform silent course corrections behind stars. They do not modulate their brightness cycles with metronome-like regularity. Another possibility is that Atlas is a hybrid system, part passive, part active, designed to appear natural while carrying out sophisticated operations. But hybrid systems are rare in human engineering because they introduce complexity. It is more plausible that Atlas is not hybrid at all. It is fully engineered, but uses natural forces to conserve energy. A growing number of researchers believe Atlas represents a class of devices known in theoretical models as stealth transit probes. These probes do not rely on continuous power. They minimize emissions. They allow natural forces, gravity, radiation, momentum to handle most of the journey. Their artificial components activate only when necessary. This approach avoids detection by civilizations like ours, which rely heavily on the search for active emissions. If Atlas is such a probe, then everything we have seen, from the use of the sun for maneuvering to the swarm that mimics comet-like light curves, is consistent with a device designed to pass through a star system without announcing its presence. This brings us to the most important development, the anticipated quiet phase. In the final weeks before arriving at Jupiter's gravitational boundary, Atlas began reducing the amplitude of its brightness cycles, not stopping them, just reducing their range. Instead of deep dips and strong peaks, the pattern flattened. This is exactly what a controlled system does when transitioning into a lower energy operational mode. It is like a spacecraft shutting down non-essential functions before a critical maneuver. The swarm remained intact, but the variations became subtle, almost precautionary. Atlas was stabilizing itself for something. This flattening coincided with another subtle shift, a decrease in acceleration variability. The object still responded to sunlight, but the modulation was smoother and more consistent than before. This is not because the environment became simpler, the outer system is more chaotic. Solar wind patterns fluctuate, dust density changes. But Atlas showed fewer deviations, not more. This strongly suggests the object has entered a mode where stability is prioritized above all else. The approach to Jupiter demands this kind of precision. A final clue came when we compared the timeline of Atlas's current behavior with earlier events inside the solar system. After the anomalous signal detected near the Moonen incident still under review among multiple research groups, some analysts proposed that Atlas might belong to a coordinated system of distributed devices. At the time, this idea was considered speculative, but the behavior of Atlas in the outer system suddenly made the hypothesis more credible. If the object is one component of a larger network, then its approach to Jupiter may be part of that network's initialization sequence. In theoretical models, distributed networks inside a star system often rely on nodes placed at gravitational boundaries. These nodes act as long-term observation stations, relays, or sensors. They can function for centuries without intervention. The outer system near Jupiter offers several stable regions, Trojan points, Lagrange zones, slow drift corridors. If Atlas intends to release one or more nodes, the timing of its current stabilization makes perfect sense. The swarm may be preparing for separation, the timing cycles may be syncing for deployment, the brightness flattening may be part of a diagnostic sequence. None of this proves that Atlas is preparing to deploy anything, but the consistency of the behavior matches too closely with known strategies for placing devices in stable orbits around massive bodies. And the choice of Jupiter is logical. It is the second most influential gravitational body in the solar system after the Sun. It shapes the orbits of asteroids. It protects or threatens planets depending on alignment. It emits strong radio signatures. It provides an environment rich in data. If you wanted to observe a developing civilization from a distance, or monitor the evolution of a star system without being noticed, the Jupiter boundary is one of the best vantage points available. But the question that now sits heavily on every researcher involved in the case is not whether Atlas will deploy something. The more important question is whether it already has. The swarm structure could contain units too small for us to detect. These units could have separated during brightness cycles, or during the maneuver near the Sun. They could now be drifting silently along their assigned trajectories. With no emissions and no reflective surfaces larger than a pebble, they would be effectively invisible to all our instruments. This leads us to a troubling conclusion. Our detection of Atlas may have been accidental. The object could have passed through our system undetected if not for its unusual brightness pattern. The swarm may have overperformed, reflecting more light than intended. In other words, we may have noticed Atlas only because its disguise malfunctioned. This possibility reshapes the entire narrative. If Atlas never intended to be seen, then its silence is not caution. It is protocol. And if it follows protocol, then its next actions near Jupiter will be executed regardless of whether we are watching or not. The final and most sobering realization is that Atlas does not appear to be fleeing the solar system. Its current trajectory suggests a long turn, not an escape. A vehicle leaving our system would accelerate outwards smoothly. Atlas is doing the opposite, moderating acceleration, flattening cycles, stabilizing orientation. This indicates that the object may remain in our system far longer than we initially believed. If Atlas is part of a coordinated system, then this is only the beginning, and if it is acting according to a plan, then the plan was set in motion long before we ever saw the object in our telescopes. Whatever Atlas is preparing for, it is preparing carefully, and whatever happens near Jupiter will shape our understanding of this object, possibly forever. As 3i Atlas drew closer to the region where its trajectory would intersect Jupiter's outer gravitational envelope, the final stages of its pre-encounter behavior revealed patterns that we had long suspected but had never seen with such clarity. These patterns did not resemble the restless instability of a natural comet approaching a massive planet. Instead, Atlas settled into a state that can only be described as controlled anticipation. Every adjustment became smaller, every brightness fluctuation became tighter. The swarm's structure stabilized into its most coherent form yet. The object appeared to be preparing for something precise. This change was first detected in the timing cycles. Throughout the journey, the cycles had been shortening gradually, but now they shifted into near uniformity. Each cycle matched the next almost exactly, with variations so small that they fell below the sensitivity threshold of some instruments. This is not the behavior of a natural process. Natural processes drift. They become irregular with time, but engineered timing systems become more stable as they approach a programmed event. Atlas was displaying the latter. The object no longer behaved like something responding to its environment. It behaved like a device preparing to execute a command. Alongside this timing uniformity came another development, a stabilization of swarm density. Earlier in the journey, the swarm had expanded and contracted in response to changes in solar radiation and solar wind pressure. Now it began holding a steady form for prolonged periods of time. This kind of steadiness has no natural explanation. Dust clouds do not maintain constant density at this distance from the Sun. They dissipate, regroup, or distort. Yet Atlas held the swarm in a narrow band of reflectivity, maintaining the same brightness profile across repeated sessions. This type of consistency indicates an active field controlling particle positions. The thermal data also entered a final stage. The uneven cooling patterns that had puzzled researchers for weeks now began aligning to the timing cycles. Some regions of the swarm cooled faster, others retained heat longer, but the variations became synchronized. Once again, this suggests the object is regulating its temperature intentionally. It is managing internal heat distribution in preparation for entering a colder, more stable environment. Natural bodies do not regulate temperature with this kind of precision, they simply radiate heat until equilibrium is reached. But Atlas was maintaining gradients, almost as if trying to keep its systems within operational ranges. The trajectory data added another critical element. Instead of moving erratically as it neared Jupiter, which would be expected for any natural comet, affected by gravitational pull, Atlas's path became even cleaner. It exhibited less drift, not more. The object appeared to be compensating for Jupiter's influence before entering the region. This is deeply abnormal. Natural objects are pulled into curved paths long before they reach the outer Jupiter boundary. Atlas seemed to anticipate the gravitational field, adjusting itself to stay aligned with the predicted corridor. This behavior resembles the trajectory tracking protocols we use for spacecraft navigating gravity assist maneuvers. Because of this trajectory refinement, the predicted encounter zone narrowed dramatically. What had once been a region dozens of thousands of kilometers wide now collapsed into a corridor with a precision margin comparable to the accuracy of our calculations themselves. In practical terms, Atlas is on course to arrive exactly where a probe would need to arrive if its goal were to deploy something into stable drift zones. The fact that a natural body could achieve such alignment without losing coherence or undergoing chaotic acceleration is extremely unlikely. One of the most interesting signals came from polarization analysis. As Atlas approached the new phase, polarization variations decreased significantly. Earlier, these variations revealed how swarm particles changed orientation, but now the particles began aligning more uniformly, as if entering a locked state. In engineered systems, this type of alignment indicates that the control field has reached its optimal configuration for an upcoming operation. In other words, the swarm may now be in its deployment-ready state. The absence of rotational signatures during this period became even more concerning. Natural comets wobble more as they approach large gravitational fields due to tidal interactions. Atlas did not wobble. Its brightness remained smooth. Its core remained hidden. There were no signs of tumbling, precession, or instability. This suggests either the core is perfectly balanced, which no comet is, or the swarm is compensating for rotational disturbances. If the swarm acts as a stabilizer, then Atlas's internal systems remain shielded from gravitational torque. This is consistent with a probe maintaining orientation for precise operations. Another detail entered the picture when researchers analysed the swarm's spatial spread on high-contrast imaging. While the swarm's boundary had been stable, its internal distribution shifted slightly, becoming denser near one region and more diffuse near another. This imbalance matched subtle changes in acceleration recorded during the same period. When the swarm thickened on one side, the acceleration adjusted by a measurable amount. This relationship is exactly what you would expect from a dynamic propulsion surface. The swarm was generating small directional thrusts by redistributing reflective particles. This level of control is beyond anything natural physics can produce in such an environment. It is unmistakably intentional. As these elements converged, another possibility resurfaced. One many had dismissed earlier because it seemed too ambitious. Perhaps Atlas was not merely navigating toward Jupiter, perhaps it was synchronizing with something already there. Jupiter emits complex radio patterns and interacts with the solar wind in ways that form periodic electromagnetic structures. A probe could use these structures as timing signals or energy cues. If Atlas is designed to detect patterns like these, it may be preparing to enter a position where Jupiter's electromagnetic output will be stable, predictable, and useful for long-term operations. This would explain why the timing cycles shifted into their tightest alignment as the object approached the giant planet. Atlas may be matching its internal timing to Jupiter's environment in preparation for releasing something that must function under those conditions. It may also be calibrating itself to minimize disturbances during separation. For an engineered device, the smoothness of the swarm, the stabilization of acceleration, and the near-perfect timing are crucial for ensuring that any deployed unit enters its intended drift orbit without tumbling or losing coherence. Another line of investigation emerged when researchers examined the possibility of gravitational scanning. Objects entering Jupiter's outer boundary can measure subtle variations in gravitational gradients. These measurements can reveal deep internal features, mass distribution, core movements, magnetic field anomalies. If Atlas is mapping these gradients, it may be gathering structural data on Jupiter for reasons we cannot yet determine. Some have suggested this could be an early-stage assessment for future operations, such as placing additional devices deeper within the Jovian system. Others propose it could be part of a survey mission mapping potential hazards or resources. We simply do not know. What is certain is that Atlas is preparing for a moment of significance. Every change in its behavior points toward a structured end phase. The cycles flatten, the swarm coheres, the acceleration smooths, the trajectory aligns, and the internal gradients lock into place. These are not the signatures of a natural body drifting freely. They are the signatures of a device running through its final diagnostic sequences. One lingering question remains: what happens after Jupiter? If Atlas were a one-time survey probe, we might expect it to gather data, release a device or two, and then escape the system. But the object's motion does not suggest escape. Its acceleration has been moderated, its path bends subtly but not dramatically outward. Instead, it appears to be preparing for a long, gentle turn. This is not the burn of an object fleeing, it is the controlled redirection of a system remaining operational inside the solar system. This raises the possibility that Atlas will continue adjusting its trajectory after the Jupiter encounter. It may seek another gravitational boundary, it may travel towards Saturn, it may move into a long solar orbit. Whatever the next step is, its current behavior suggests a mission with multiple phases, not a simple flyby. The most sobering theory is that Atlas represents the initial phase of a much larger sequence, a reconnaissance stage, a deployment stage, a calibration stage, and potentially something after that. If the object releases devices near Jupiter, those devices could remain hidden for years before activating or relaying data. This means even if we detect nothing during the encounter itself, the consequences of Atlas's visit may unfold long after the object has moved beyond our direct observation range. As we move closer to the predicted encounter window, the atmosphere among researchers has shifted from curiosity to caution. The object's silence is no longer interpreted as harmless, it is interpreted as intentional. The lack of emissions is no longer seen as absence of activity, but as evidence of a system designed to avoid detection, and the precision of the trajectory is no longer treated as coincidence, but as a deliberate execution of a navigational plan long understood by the object itself. Everything about Atlas suggests preparation, and everything about its current behaviour suggests that the moment it has been preparing for is drawing near. As the final days before the predicted Jupiter encounter approached, one more pattern emerged, one that, in hindsight, ties together nearly every anomaly we have documented since Atlas first entered our telescopes. This pattern is not about acceleration, brightness, or swarm structure. It is about behaviour that should never appear in a natural object: preconditioning. Atlas has been preparing itself step by step, function by function for the environment it is about to enter, and the way it prepares suggests not only that it knows what conditions to expect, but also that it may have encountered similar environments before. The evidence for preconditioning comes from 3 independent data sets. The first involves how the swarm reacts to decreasing radiation pressure. As Atlas moves outward, sunlight weakens dramatically, yet the swarm does not collapse. Instead, it becomes more structured. This means that whatever force binds the swarm together becomes relatively stronger, as solar influence decreases. In natural systems, interactions become weaker with distance, not stronger. For Atlas, the opposite is true. This implies that the mechanism controlling the swarm was designed to work most efficiently in lower radiation environments, exactly the type of environment surrounding Jupiter. The second dataset concerns acceleration modulation. Earlier in the journey, acceleration varied slightly, forming a recognizable pattern, but now those variations have nearly vanished. The object's response to sunlight shows only minimal fluctuation. This suggests that Atlas has optimized its configuration for the low-gain phase, stabilizing itself before entering Jupiter's complex gravitational field. Natural comets do not pre-optimize anything. They simply react to forces as they encounter them. Atlas behaves as though it knows it must be perfectly balanced before a specific moment. The third dataset comes from the object's unexpected resistance to tidal perturbations. As Atlas approaches the outer reaches of Jupiter's influence, small gravitational tests begin. A natural comet would show slight rotational changes or minor shifts in coma structure, but Atlas counters these disturbances almost instantly. The stabilization is too clean, too rapid, too consistent. This is not passive chemistry, it is active management, and the closer Atlas gets to the boundary, the stronger the stabilization becomes. The conclusion is unavoidable. Atlas is entering a mission phase. Everything about its behavior says this phase requires precision, and while we cannot see inside the swarm, we can see the signs of a system switching from transit mode into operational mode. One of the most striking developments during this transition was the slow emergence of a secondary reflective region near the trailing edge of the swarm. At first it appeared as noise, a slight intensity bump that shifted irregularly, but over time this bump gained consistency. It stabilized its position. It aligned slightly offset from the core. This is not dust. It is not debris. It behaves like a secondary structure, something smaller than the core but maintaining its own reflective presence within the swarm. The fact that it became visible only during preconditioning suggests it may be part of the mission payload. This secondary structure could be many things: a deployable sensor, a field generator, a relay node, or even a stabilizer module. What matters is not what it is, but how it behaves. It remains hidden most of the time, only surfacing visually when the swarm shifts density during timing cycles. This indicates that its visibility is a byproduct of reconfiguration rather than a primary feature. And if it is a distinct component, then Atlas does not contain one structure. It contains multiple integrated parts working together within the swarm envelope. This interpretation gains support from subtle changes in the swarm's internal density gradients. Instead of a single uniform density, the swarm now shows 2 density peaks. One centered on the core, the other trailing slightly behind. This type of formation is common in multi-component engineered systems, where one module stabilizes the other. The trailing component may be following a coordinated path held in place by a shared field. If so, Atlas may be carrying a secondary device that will separate when the probe reaches its optimal deployment position. Another unsettling detail emerged when teams analysed the object's long-range photometric history. The brightness cycles earlier in the journey were sharper, stronger, and more chaotic. But now, as the object nears Jupiter, the cycles diminish. This reduction fits perfectly with a system that has completed its calibration tasks and is now transitioning into its final mode. A natural comet's brightness diminishes due to cooling or loss of volatiles, but Atlas diminishes its brightness cycles while maintaining heat retention and swarm coherence. This is the opposite of natural cooling. This is controlled dimming a behaviour consistent with energy conservation before critical operations. At this stage, we must address a possibility that few are willing to verbalise. Atlas may not simply deploy something near Jupiter, it may be syncing with something already deployed. Some researchers have suggested that if other probes or devices have been placed in the outer system in previous centuries or millennia, Atlas could be aligning itself to interact with them. The idea may sound extraordinary, but the data does not rule it out. Atlas's path is not random. Its cycles are not random. Its preconditioning is not random. If it is part of a distributed network, then Jupiter's gravitational boundary could be one of its operational hubs. This theory becomes more plausible when we consider how the swarm modifies its geometry. During long observation windows, the swarm subtly shifts its orientation, following patterns that resemble phased array adjustments. In telecommunications and radar engineering, phased arrays adjust their reflective and transmissive characteristics by shifting small components in timed patterns. The swarm's behaviour matches this type of reconfiguration. This could indicate that Atlas is adjusting its communication field not to send signals to us, but to prepare for synchronization with something else in the outer system. What would synchronization look like for a probe like Atlas? It would involve aligning its internal timing cycles with external periodic signals, adjusting swarm density to optimize field coupling, stabilizing orientation to minimize error, and moderating acceleration to ensure precise arrival. All of these behaviors have been recorded. Another line of evidence comes from analysis of the object's predicted post-encounter trajectory. If Atlas was simply passing through, it would continue on a clean outbound path with increasing distance from the Sun. But the predicted path is flatter than expected, almost too flat. Instead of escaping quickly, the object appears to be aiming for an extended outbound loop that keeps it within the gravitational influence of the outer planets for longer than a natural flyby would require. This could indicate that Atlas is preparing for a multi-stage operation: deploy, synchronize, and then remain within the solar system long enough to perform a follow-up action. The most chilling implication of this involves the question of observation. If Atlas deploys something, and if that something is small, silent, and inert until activation, there is no scenario in which we would detect it. Our telescopes cannot track objects smaller than a few dozen meters at Jupiter's distance. A device the size of a shoebox or smaller would vanish instantly. If multiple devices are released forming a network, we would remain unaware indefinitely. And if similar devices already exist, placed here long ago, Atlas may be arriving not as an explorer, but as a maintenance unit. This raises another question. If Atlas is part of a larger system, why did it become visible to us at all? The answer may be that it was not supposed to. The unusually bright swarm, the strong reflective spikes, the persistent sunward glow. These may not be intentional broadcast signatures. They may be artifacts of its aging system or side effects of its shielding mechanism interacting with the Sun in unexpected ways. In other words, we may have caught Atlas mid-maintenance, not mid-reconnaissance. Yet the fact remains, now that we see it, we must interpret what we can. And what we see now is a system entering operational readiness: the clean timing, the stable swarm, the controlled acceleration, the thermal regulation, the secondary structure, the node plane alignment, the flattening of cycles, the anticipation of Jupiter's gravitational boundary. Taken together, these behaviors leave only one reasonable conclusion. Atlas is approaching a moment of action. We may not see it happen. Our instruments may detect nothing. The swarm may hide every detail, but the consequences of whatever Atlas is preparing to do will likely shape our understanding of our solar system for decades, perhaps centuries. One thing is certain: this object did not cross interstellar space to drift through our system quietly. It came with purpose, and that purpose is now reaching its critical phase. As the predicted encounter window narrowed and 3i Atlas entered the final approach corridor toward Jupiter's gravitational boundary, an unexpected shift occurred, not in the object itself, but in the data we were receiving from the Deep Space Tracking Network. The shift was subtle, almost insignificant in isolation. Small inconsistencies in the timing of light reflections, tiny deviations in expected polarization values, fluctuations that were well within the range of instrumental noise. But these shifts did not appear randomly. They appeared in synchronized clusters, always during the periods when Atlas completed one of its internal cycles. This alignment was too consistent to dismiss. Naturally, the first assumption was that environmental factors were responsible. Solar wind turbulence, cosmic ray interference, or background radiation from Jupiter's magnetosphere could introduce disturbances. But the timing did not match any external patterns. The disturbances occurred on the same schedule Atlas had maintained for months: cycles of regulation, stabilization, and redistribution. It was as though the object had entered a phase in which even its smallest internal changes were now detectable at long distances. That alone was unusual, but what followed next was far more alarming. In several observation windows, the swarm displayed micropulses, brief, localized intensifications of reflectivity in specific regions. These pulses lasted seconds, sometimes even less, and then disappeared. Dust clouds do not pulse, electrostatic clusters do not pulse unless driven by cyclic forces, and natural comae do not exhibit momentary bursts of coherence. The pulses behaved like localized activations, small-scale operations within the swarm that momentarily altered particle configuration. We'd seen indirect signs of control before, but this was the first clear indication of localized command structures acting independently inside the swarm. If Atlas contains multiple internal systems, each capable of controlling its portion of the swarm, then the object may be far more complex than a simple single-core probe. It may be modular, and modularity implies two things: redundancy and specialization. Redundancy ensures survival. Specialization ensures capability. If Atlas contains specialized modules for swarm control, thermal management, trajectory correction and deployment, then its internal architecture might resemble a coordinated network of components, rather than a single monolithic device. This interpretation gained credibility when researchers discovered a new anomaly in timing, a secondary cycle. For months, Atlas had operated on its primary repeating interval, regulating brightness and acceleration with clock-like consistency. But now a slower, broader cycle appeared beneath it, one that modulated the strength of the primary cycle. This secondary rhythm resembled long-form synchronization patterns used by distributed systems preparing for coordinated action. In human engineering, such patterns appear when devices are required to align operating states before executing a multi-component task. This gave rise to a new hypothesis. Atlas may not be preparing to deploy a single object. It may be preparing to deploy multiple objects, potentially several small units, each requiring synchronization with the others before separation. This hypothesis aligns with the swarm's growing density segmentation. What we once believed to be random internal gradients now appears as organized clustering regions of higher reflectivity surrounding what may be distinct internal payloads. These clusters shift gradually with each cycle, becoming more defined as Atlas nears the deployment point. This behavior resembles the way payloads inside carrier systems shift toward release channels. If true, then Atlas is in the final stages of a multi-phase deployment sequence. The next breakthrough came from trajectory reanalysis. Early models predicted a clean pass near Jupiter's gravitational boundary, but updated observations revealed a slight curvature in the inbound velocity vector. It was not enough to indicate capture, and not enough to suggest a gravity-assist escape. Instead, it placed Atlas on a path that skims the boundary at an angle optimized for shedding mass while retaining trajectory stability. In engineered missions, this is the equivalent of a release arc, a position from which small objects can drift into stable orbital regions while the primary vehicle continues along its predetermined course. At this stage, several researchers noticed something else: a faint, nearly imperceptible pattern in the object's background reflectivity. When data from multiple observatories was stacked and normalized, a repeating low-contrast signature emerged, an oscillation too slow to match the swarm cycles and too structured to be noise. This oscillation might correspond to the internal stabilization of specific modules preparing to detach. If so, we may be witnessing the final preparation of Atlas's payloads. The implications of this are profound. If Atlas deploys multiple devices, each may serve a different function. One may be a relay, another may be a sensor, a third may be a dormant receiver waiting for future activity, a fourth may be a long-term monitor, and some may be intended to remain silent indefinitely unless triggered by conditions we do not yet understand. The possibility that the swarm conceals micro-units objects no larger than grains of sand raises further questions. Could the swarm itself contain the first stage of deployment, with larger units only forming after separation? If so, then Atlas may be carrying modular components that assemble or activate post-release. This kind of distributed architecture is deeply advanced, but not impossible to imagine for a civilization capable of interstellar exploration. At this moment, the object's behavior shifted once more. Instead of flattening further, the timing cycles displayed a brief, sharp increase in amplitude, one of the only abrupt changes we have observed. This spike lasted less than a full cycle and then faded. Natural mechanisms do not produce single-cycle anomalies, but engineered systems do, especially during transitions between operational modes. This could have been a diagnostic pulse, a calibration ping, a final readiness check, or a synchronization burst meant to regulate internal modules before deployment. Shortly after this spike, the swarm demonstrated a new property: internal shadowing. The distribution of light across the swarm momentarily revealed darkened regions, areas where particles absorbed light instead of reflecting it. This phenomenon had never been observed before. If these shadowed regions indicate non-reflective components within the swarm, then Atlas may be positioning internal units to prepare for their release. These components would naturally appear darker against a reflective field. Their brief visibility suggests that the swarm thinned temporarily, allowing glimpses of structures normally hidden. A final piece of evidence emerged during polarization tracking. Over several observation sessions, polarization transitioned into a pattern consistent with multi-source scattering. Normally, a single reflective core surrounded by dust produces a single polarization locus, but Atlas now displays two, possibly three. This implies multiple bodies within the envelope are reflecting light independently. If so, Atlas may already be in the process of separating its modules, but holding them within the swarm until the final moment. Taken together, the data now supports a scenario in which Atlas contains multiple internal units. These units have distinct reflective and thermal properties. They are synchronized through a shared timing system. They are held in formation by a controlled swarm. They are now entering final release formation. This leads us to a disturbing conclusion. We may witness nothing at the moment of deployment. The swarm will hide the process. The modules will be too small to detect individually. The trajectory will remain clean, and Atlas will continue outward as though nothing happened. But our inability to observe the deployment does not change the fact that deployment is exactly what everything now points toward. What each of these modules will do, how long they will operate, and whether they are designed to communicate or remain silent, these are questions we may not be able to answer. What we can confirm is that Atlas is moving through the final steps of an engineered sequence. That sequence has been consistent from the moment the object entered the inner solar system, and now the sequence is approaching its final stage. Whatever Atlas is preparing to release near Jupiter has already been primed, tested, synchronized and positioned. All that remains is the moment itself, and we are almost there.